whose internal supervisor is Danijela, and external supervisor, I'm not sure if they need to join us.
I don't think
Because it's like, she's in Hawaii. Anyway, I'll just mention it's Jennifer Graham, Forest Fan, with the program specialist, statewide, Department of Land and Natural Resources, Hawaii. Over to you, Andreas.
Thank you so much, Peter. Thanks for facilitating things, and thank you also, Laura, for facilitating. Good afternoon, everyone. My name is Andreas Jankovic, and this is my project, Back in Black. This summer, I worked under Dr. Danijela in the Urban and Settled Landscapes Lab, conducting VSP survey sampling in black ash swamps and wetlands. I'll be presenting my findings about carbon and disturbances in black ash associated stands around Lake Simcoe. The core question I'm asking, how much above ground carbon is currently stored in these mixed wetland forests, and how can I model large-scale mortality, simulate what these stands would look like to emulate full stand collapse? I'll quickly cover the ecological and cultural context, explain the field data and methods, then walk through the main results and mortality scenarios, and then end with possible recommendations. So this is the situation. As you can see from these pictures, these are what once dominated black ash wetlands look like right now around Lake Simcoe, and how a majority of these black ash swamps look like right now all across southern Ontario. What you see here, these tall, dead ash snags, is the result of emerald ash borer, or EAB. These areas are saturated systems where black ash historically structured the canopy in hydrology. These systems are now in transition with canopy openings, shifting water tables, and large deadwood inputs. Understanding the carbon in this changing environment is the undertaking I'm attempting to do. Why do these black ash associated wetlands matter? Black ash historically dominates or co-dominates lowland forests, riparian corridors, and wet depressions across the Great Lakes St. Lawrence region. These sites are wet, flooded for long periods, and often inaccessible to typical upland tree species. This map here showcases the extent in which black ash can exist in North America. Ecologically, black ash type wetlands help stabilize stream banks, flooding and water levels, and support diverse plant and wildlife communities. Once black ash disappears, you lose a prolific species as well that have co-evolved with it. Culturally, black ash is a keystone for many Indigenous nations. It's central to basket-making traditions, food gathering, storage, and ceremony. The soft, corky bark and pliable nature of its wood have made it perfect for such practices. Unfortunately, it has also made it very attractive to a certain invasive beetle, which I will touch on in a moment. So when we lose mature black ash, it's not just an ecological change, it's also a loss of living cultural infrastructure. Wetlands occupy a relatively small area in a global context, but they store a disproportionate amount of carbon, especially in their soils. Persistent saturation limits oxygen, slows decomposition, and allows organic matter to build up over time. In forested wetlands, carbon is split between above-ground pools or conglomerates of live biomass and coarse woody debris, and below-ground pools in soils, roots, and buried wood. My project focuses on the above-ground carbon only, because that's what the VSP data captures directly. But it's important to remember that the soil pool is probably several times larger, so any disturbance of these systems has implications beyond what I modeled. So, in terms of the impact, emerald ash borer, or EAB, which is the shiny green beetle you can see on the slide, has been in North America since the early 2000s and is extremely widespread. Black ash is often cited as one of the most vulnerable ash species, with projected mortality above 90 to 99% in many regions. In Ontario, black ash is listed as endangered, primarily because of EAB. As trees die, we see cascading effects on forest structure, hydrology, and carbon cycling. In wetlands, extensive overstoring mortality and root dieback can change water table depth. The timing of saturation and soil redux conditions. That in turn affects decomposition rates and greenhouse gases influx. So EAB is not only a biodiversity issue as it decimates ash trees, it's also a carbon and climate issue too, because it kills these ash trees and it can make these wetlands into carbon sources and not sinks. In this project, I have three objectives. First, to quantify stand structure and species composition of these stands using VSP data. Second, to estimate above carbon stocks in live trees and coarse woody debris. Third, to model how stand level carbon might change under different overstory mortality scenarios of what is left in these current stands. The study area is a set of mixed lowland and riparian forests within and around the Lake Simcoe watershed in southern Ontario. I used 27 vegetation sampling protocol plots established between 2017 and 2025 as a part of a broader black ash monitoring program. Only 27 plots were used of the over 50 measured and remeasured by Emma Harper and I during July and August of 2025. As certain plots fell within or just outside the Lake Simcoe Basin, so this was done to keep the climate and physiology consistent. VSP gives a standardized 400 square meter fixed area plot where a plethora of information is recorded, but the important information I used from VSP that was specific to the study I conducted was tree species, DBH, canopy dieback, which can be a strong signifier of health, snags, down woody debris, and site descriptors. That consistency is important for carbon accounting and for linking my work to provincial monitoring frameworks. First, I quantified stand structure, basal area, stem density, and species composition using standard formulas. Basal area per hectare came from summing tree level BA and scaling up from a 400 meter squared plot. For carbon, I used Jenkins et al. 2003 allometric equations to estimate above ground biomass from DBH and converted biomass to carbon using a 0.5 carbon fraction, consistent with IPCC defaults. Side note, certain trees do have different carbon fractions, depending on species. Some contain more carbon than others. For coarse woody debris, I approximated piece volume from diameters and lengths, applied wood density and decay class adjustments, and then again converted to carbon. This gave me plot level carbon stocks for live biomass and coarse woody debris, which I then summarized across all 27 plots. Unfortunately, I could not make the study only on black ash in these plots as the majority of them are completely dead, so a stand-wide approach is best. To explore vulnerability, I built a simple stand scale simulation. I took the mean observed above ground carbon across stands, which came out to be 84.4 megagrams of carbon per hectare as a baseline black ash type mixed wetland stand. Side note, 1 megagram is equal to 1 ton. Then I imposed three stylized mortality scenarios at time 0. Scenario A, 0% additional mortality. Scenario B, 50% additional mortality, where half of live biomass moves into deadwood. Scenario C, also 100% mortality, where there is a full overstory collapse. Deadwood decayed using a first order exponential model with a K value of 0.03 per year as a baseline, and moisture adjusted values for 0.025 for wet, 0.03 for mesic, and 0.04 for drier plots. Since it's difficult to pull this specifically from VSP data, depending on plot type, I matched the plot areas by their appropriate GPS location and matched this with imagery from databases which had 50-meter resolution maps on land physiology type. This model tracked how above ground carbon remained over 10, 20, and 50 years and converted losses to carbon dioxide equivalent emissions using the standard 3.67 factor, as carbon dioxide is atomically heavier than carbon on its own. Structurally, the stands range from relatively open to quite dense. Basal area averaged 25.2 meters squared per hectare, within a range from about 2.6 to over 40. Stem density averaged 851 stems per hectare. In terms of carbon, mean above ground carbon was 84.4 megagrams, as said earlier, per hectare, with a standard deviation of 37.7, both a wide variation from just over 6 to almost 162 megagrams of carbon per hectare, depending on the stand. Live biomass accounted for about 81% and coarse woody debris about 19%. In comparing our Ontario black ash wetlands, the mean above ground carbon was 84 megagrams per hectare, with some stands exceeding 120 to even 162 megagrams per stand. These values are right in line with or slightly higher than black ash wetlands studied in Minnesota and Michigan, which typically range from 70 to 90 megagrams of carbon per hectare. That means that Lake Simcoe wetlands are storing carbon at levels consistent with some of the best characterized black ash systems in the lake states, even though these stands I measured have little to none living black ash. Black ash is now structurally minor. On average, it's just 3.3% of stems and 1.2% of basal area, with many plots having no surviving ash. That's consistent with a post-EAB landscape where ash persists almost as remnant stems in regeneration, not as dominant canopy tree. This is simply because in these stands I measured, black ash faces a very pressure from deer, and even when saplings regrow and reach a certain DBH threshold, EAB will come back and pounce. This map here showcases VSP plots by how much carbon they have. The bigger circle or polygon, the more red it is, the more carbon there is there. Coarse woody debris stored about 15.9 megagrams of carbon per hectare, which is roughly 1/5 of total above ground carbon. The distribution of decay classes from 1 to 5 show that these stands contain both fresh mortality and long-standing legacy deadwood, with the average decay class being 2.65 across stands and 44% of deadwood being in decay class 2. This tells us two things. First, these wetlands have been accumulating deadwood for years, showcasing that EAB has been present at these stands for a long time. Second, deadwood carbon is only weakly correlated to current live biomass with a p-value just above 0.05, meaning it reflects past disturbance history rather than present stand structure. The mortality situations show how sensitive these stands can be to large-scale stand collapse. Visiting these stands and seeing firsthand how only a few species like basswood or Freeman maple are the only trees in good health, I wanted to ensure this model include all species. Under scenario A, with no extra mortality, carbon declines only modestly to 72.1 megagrams of carbon per hectare under 50 years as existing deadwood slowly decays. Under scenario B, with 50% mortality at time zero, above ground carbon falls to 45.5 megagrams per hectare, roughly a 46% reduction. Under scenario C, with complete canopy collapse, it falls to 18.8 megagrams per hectare, about a 78% reduction over 50 years. These losses correspond to roughly 143 to 241 megagrams of carbon dioxide equivalent per hectare. That's in the same ballpark as emissions associated with clear-cut harvest cycles in some upland systems, which underlines that wetland overstoring mortality is a non-trivial climate issue. This study has a lot of limitations. It only includes above ground carbon. Soil carbon was not measured and is likely much larger. The mortality scenarios are stylized. A lot of the other trees are suffering in these stands. American elm, balsam fir, white cedar, each from their respective disease and pest, which is entirely other topic that I don't have time to talk about today. My main attempt was to create a scenario of data I don't have, trying to show how these stands would behave with complete collapse, trying to recreate what would happen when EAB first arrived decades ago, along with other diseases in the past. Also, the decay constant comes from literature, not site calibration. I use a simple exponential model for deadwood decay. It's linear. I also did not model regeneration or growth. And finally, wetlands are highly variable. And this data set covers only 27 plots around Lake Simcoe. There needs to be much more research done, and the next step would be to look and compare historical data. The situation around EAB and black ash may be grim. What can we do? I always want to stay optimistic in any scenario I encounter in my life, regardless of what's thrown at me. My first recommendation is to continue strengthening monitoring of EAB impacts and decline in black ash associated wetlands, as climate change constantly pushes the limit of where EAB can exist. Second, monitoring regeneration is essential. Tracking saplings and seedling survival helps determine whether these wetlands will cover a forest canopy or transition towards shrub or open wetland states. Third, seed banking and genetic conservation are urgent priorities. The MACP Black Ash Recovery Strategy highlights that seed sources are disappearing rapidly, and preparing now preserves future restoration potential. Finally, the long-term restoration planning, such as maintaining wetland forest conditions or supporting flood-tolerant species, things that Lake Simcoe Conservation Authority already does, will help buffer the carbon loss and keep management options open into the future. And with my closing statement, before I acknowledge and thank everyone, I'd like to highlight this quote by Marcus Aurelius, a former Roman emperor and philosopher. Nature does its work. The trees, the plants, the birds, the ants, the spiders, the bees, each play its part. So why hesitate in doing yours? What this quote means to me is that the trees don't grow because they want praise, attention, or validation. They grow because that's what they are meant to do. They follow their purpose quietly and consistently, becoming as strong, as tall, and as resilient as they can. So as I close, I invite my fellow MFC class and everyone else here to emulate what trees do, to lean on what you're meant to become, to grow into the best version of yourself, and to do the work that nature and life demands of you, quietly, steadily, and with purpose. I want to thank my supervisor, Dr. Danijela Puric-Mladenovic, for her guidance and mentorship throughout this project. A special thank you to Emma Harper for incredible field partnership and logistics, and to Zoe Turner-Debs for being a great BSP crew leader. I want to acknowledge every forestry professor for their invaluable education, the entire MFC cohort I'm a part of, all the landowners and conservation authorities who allowed us to access these wetland forests, and a big thank you to Environment Conservation and Parks Canada for providing funding, and my friends and family for the continued support. Thank you. And this is my references.
So I assume that all photos were taken under strict safety protocol and don't actually lying down on train track. I'm passing it off to Mr. Canada.
I don't want to have a question about that train track. Yeah, thank you so much. I have a few questions. The first one is, about sleeping providing. So you guys, we haven't had a chance to look at this yet, but just from your observation, is there anything that is coming back?
Unfortunately, no. What Emma and I observed over the summer is that there was no new seedlings this summer. Most of the remnants are from years past, so there was nothing new this summer from black ash.
Side black. Changing the dollar or?
I actually don't think it was too wet. The summer was very, very dry. It could have been just the black ash were not dropping their seedlings, which is most likely the case, just wasn't a year for it. But it just, yeah, it was a very dry summer, so.
Yeah, my other question is, because we did something before the year, so we have no chance to look at the old data yet. But, what else is counted? What's we see? Basically, we see there.
So there is a lot of ironwood, basswood, of course. Like I mentioned in the presentation, basswood and Acer Fermani or Freeman's maple, they're doing great. Not too many other saplings. There's more so I'd say a lot of green and white ash, not specifically black ash. And then there are some conifers coming through like cedar and balsam fir. Some of the sites we would get into would be not too deep, relatively up to maybe above my knee level. What was more difficult actually was transversing to some of the sites. Some of the sites would take us about an hour and a half, and that's when we would get up to here. So water levels would be up to here just to be able to cross a river or whatnot to get to a certain site. So it's very difficult. I just want to emphasize how difficult it is sampling in black ash or just simply in swamps and wetlands. Not a lot of people want to do it.
Not many people have. Thank you.
It's a good job to tell them. More questions for Andreas. Randy.
Thanks, Andreas, a great overview, and I know you want to have. Well, very good, so this is an extension sort of what Danijela was asking, and basically, and can you talk about actually address this issue of regen? You didn't see any recently, I think you said there was a past regen, like do you have a sense of how long kind of has been some regen?
Yeah. So there's some regen maybe from 2, 3, 4 years ago. Yeah, for sure. There's much bigger DBH trees. Like there's 8 DBH, 10, 12, whatever. The main issue obviously is that once I can't name off the top of my head a certain threshold of what DBH it is, but no, I mean once the black ash reaches certain DBH, it becomes just perfect snack for EAB to come in and just pounce on it, right? So it's just a constant cycle of trying to get away from deers, and then also EAB comes in and just pounces on the tree, right? So
well, so that's actually where my question came from, because I guess I don't like the word pounce. I understand why you use it, and I certainly I think we feel that that's the way it is, but I'm wondering, has there been any evidence of pouncing?
Yeah, I mean, in a lot of the plots we were at, there was just presence of EAB, emerging from the trees. So
right, so
yeah.
It's still there on site.
Yeah, on not all sites, but on some sites for sure.
Okay. You also mentioned there was evidence of low mortality. Do you have a sense of how long that is?
It could have a lot of these stands could have been around the 2000s, around the same time that EAB came through. But there's legacy of the main reason I did this project was that there's a legacy of a lot of other dead trees. Obviously with like Dutch elm disease, that was even before, and we encountered a lot of dead elm there as well, right? So it's kind of a kind of gloomy situation because all the trees in that area, most of them are suffering, like white cedar is suffering from like amarillo rot, or I might be pronouncing wrong. Balsam fir also has like the spruce budworm, and I mean there's just it's kind of a messy situation in those wetlands, right? So
Sometimes, entomologists, when people ask me to come in and what's wrong with my 200 trees. And yeah, I can see different agents that are there, but often it's a relationship to stress of the tree. So let's move PAB aside, that maybe it's a unique situation, but all these other things, maybe it comes back to Daniel's question about site and changes and stress factors that are ongoing that maybe don't have to do with PAB alone.
Yeah,
Would you agree or disagree? I guess that's the question.
I guess I would agree because it's just like climate change. Climate change is it's making everything just worse as you know as the level of where these pests can exist. It'll just keep moving more north, so we have to monitor and track where it is, right? So.
And I kind of like the last statement, but I couldn't help but reading Marcus Aurelius to sort of say, yeah, what about the beetles and the insects and all the other things that have in that tree? So, yeah, appreciated it. Thanks very much.
Thank you.
Thank you, Sandy, and we have Dr. Thomas.
First, one little comment, trees do differ in their carbon.
Yes.
Concentrations, I believe we pointed out, but about 1 minute to look up. We have published data based on, and the value for black ash was 47.
Yeah.
So it doesn't take too much time, and then it's a big difference in the money.
Yeah.
So that would be worthwhile. Question, in white ash and green red ash, there is genetic variability for resistance to EAD. And so you find about 1% of stems in natural populations that you have the there's also the genetics has been worked out, it's a single locus, so it's very easy to read. I don't believe that this has been found in black. So the question around this, if you've been to a bunch of natural stands, did you see any large black ash that were among, why you find these resistant ones, and finding this single individuals who are surviving from what's detecting destruction?
So far, no, but the goal is to find that. I read a study, or it was more sort of article about how in Oregon, that's what they're doing with a lot of green ash and white ash trees, right? I'm sure you probably read it. How they're planning, and they're planning as many as they can to figure out where, if they can create one that is actually completely resistant to EAB. I mean, a next step would try to do that black ash. I mean, it's kind of not realistic, but yeah, it's an unfortunate situation. I haven't seen it. I don't think Emma's seen it. Yeah, like a resistant large black ash tree. I think the main goal of when you find a super large black ash tree is to market for seed collection. That's one of the important things to do for sure. See if it could possibly be resistant.
So that the
Hang on.
it's for the lake seems we definitely didn't work out. But fortunately, in this time period, which we didn't data set that we have, we came across the three ones with the same counties. But we continue something this summer in this area, so we will have a little bit better understand. The lake seems for intentional. That's the good thing.
Thank you. Okay. More questions? Fair enough.
This is just more a comment, and instead of like, from Calgary, black ash was a very popular tree, it was a good fat tree 20 years ago. And then cotton psyllid came and wiped out 99% of them. I'm sure Sandy would give you more of that. But a different insect came through. So you have EAB, it's not in Calgary yet, we're protecting it. But then 20 years ago, all of our black ash was built from cotton psyllid. So it's I guess the complication, like you mentioned, in trying to solve problems in isolation, and just the limitations of looking for species and potentially respond broadly when there's all these other factors.
I mean, yeah, it kind of goes with black ash physiology. Like the bark is just corky. It's the bark, the inner xylem, like it's soft. It's a very soft tree. Most pests can just eat away at it, right? So
More questions, Max?
Great job, Andreas. Love your
Thank you.
pictures. Never get to one together. Yeah, I was just wondering, like, we're seeing, I guess, this kind of like transition of this forest type and this ecosystem as we see this huge reduction of black ash from the landscape. I'm wondering if you're seeing almost any observational trends and patterns that you think might, I guess, change the direction of these forests. Like, is there any species that's really starting to dominate? Anything that's starting to stand out? You've seen areas that like might have at one point been swamp, but are now sort of drying out, or areas that dry that made it wetter.
Yeah, so it's kind of skewed because the summer was very dry. But it's more so just seeing what's left over. You know, what Emma and I mostly observed was that a lot of basswood and a lot of Freeman maple around in those plots that we did sample. It's different in different areas, of course. They're just emerging through, they're fine. Canopies are perfectly healthy. So that's a very optimistic and plus side of things. But again, that's just left over. When you lose black ash, comparing like a plot in Toronto that would have used to have black ash, I'm not going to bring like the scientific part of it, but when we did the VSP plot on a plot that was just dominated by Freeman maple, it was only about 45 ground cover species compared to even when these black ash stands are dead, they're plus 90. So you lose half of your biodiversity when the black ash disappears, right? So.
Four.
Yeah, so you said that you are seeing a lot of like white and greenhouse, but like in there recently you're seeing more of those as opposed to that.
Yes, because there are bigger, there's more white and green ash that are healthy in those specific stands in Lake Simcoe that are okay. I wouldn't say completely healthy, but that's the main reason. So they've been dropping their seedlings for countless years, right? Main reason.
Any discussion, more questions for Andreas? Okay, thank you, Andreas.
Thank you.